lecture 11, part 1, and it's the first lecture after the midterm, and we're going to move on to a completely new topic called unsupervised learning. But before that, let's recap what is supervised learning. So basically what we did before the midterm for half of the summer, and the idea is we're given the data and we're also given the labels. So we need to use these to figure out some kind of relationship between the features and the labels so that when we are given new test data, we can use the same relationship to predict these labels. So there are two major ways of doing this. One is called discriminative supervised learning, and we just directly estimate these probabilities, estimate a function that represent the labels belonging to a particular class given the features. And the opposite way is called generative supervised learning, where we estimate these probabilities to generate these features given the labels, and then we use Bayes' rule to classify. So let me give you an example. And I know you are not interested in this because the final is not cumulative, but let's talk about this very, very quickly anyways. So there is one generative method called naive Bayes, and we're basically computing the probability that a label belongs to a particular class, say 1 here, given the features. So we can use the definition of conditional probability to rewrite this expression as the ratio between the two, and we can expand the numerator as a product of the probabilities in the conditional probability table. And we actually do the same thing for the denominator. This is just the sum of the term with y is 1 and with the term y is 0, and then you can expand each term as the product. And in any case, with a lot of algebra, we can convert this into this form, 1 plus exponential of minus and the sum of a bunch of log terms. And I guess you can see where we're going. We're going to write it in the same format as the logistic regression. So here, if you compare these two expressions, they look the same, except for this log prior probability ratio is like the bias, and these log likelihood ratios, they are like these weights. And remember, each one of these is corresponding to only one feature. So one feature here. So these things are basically like weights, although it's kind of non-linearly dependent on the x. So basically, we're estimating the same thing, except for we are estimating them differently. So here we are just directly estimating these prior probabilities and the likelihood, the conditional probabilities, and then we perform some algebra to convert it to the bias. And here we're directly estimating the bias and also the weights. So these methods kind of look the same, but again, they are just estimating these things differently. Okay, and at the beginning, we talked about generative adversarial networks, and I think at that time, most of you are not familiar with neural networks, and now you are familiar with neural networks, so I think it's a good time to recap what happened, and I guess now you understand more what's happening. So the main idea is actually still the same. We have two parts, just two neural networks. One network is the generative part, and the input is random noise, and output is fake images. And the other part is the discriminative part, and it just separates the real and fake images. So let me show you a diagram, and then I think you can understand what's happening. So here we have the training set of real images, and then we have the random noises. So it's basically just random pixel values. And then it goes through this convolutional neural network. So it's actually a convolutional neural network, but we are calling them deconvolutional neural network. And here, this is also a convolutional neural network. And we just combine them. We use the input of this generator, and we put it into the discriminator and we combine it with the real training set, and then we can classify whether the images are real and fake. So as I said, if we train them, this neural network will get better and better at discriminating these two types of images, and this network will get better and better at generating fake images. So the way we're going to train them is, of course, gradient descent, but it's slightly more complicated. So the cost function is more complicated to start with, and then the gradient descent steps are a lot more complicated for all of these weights. So I have an image here that talks about the weights and the gradient descent step. It's not very important, and I put the link to the original paper on my website already. But basically, for these complicated structures, you use a package to estimate these weights anyway, so you don't need to implement these from scratch anyway. So you only need to design the network structure for these two convolutional neural networks, and then you put it through a package, and then it will estimate the weights for you. So that's actually all I want to talk about. And now let's move on to actual unsupervised learning. So the main difference between supervised learning and unsupervised learning is that we are not given the labels. So maybe it's hard to provide the labels, or maybe it's just we don't have labels. So, but don't confuse this with the Bayesian network. So Bayesian network, we are just calling the labels one of the features. We still have the training data for these labels as features. But here, we don't actually have these labels in the training set. So in the training set, we only have features. We need to label them ourselves using some algorithm. And these algorithms are called unsupervised learning. So the most obvious application is just put them into groups. So basically, if we have kind of discrete labels, so y can be 0, 1, 2, let's say 3, and we're just putting them into groups and labeling them by the group index. So that's clustering, and we'll talk about clustering in this lecture. And the second application is novelty or outlier detection, where it's kind of just two classes. One is the normal class, and one is the outlier class. So that's the same idea. And the last one is slightly different. It's called dimensionality reduction. We'll talk about it in the next lecture. But here, let me briefly introduce this as labeling these instances by a lower dimensional feature vector. So the labels are not discrete. They are not like 0, 1, 2, 3. They are like vectors. So say 1, 2, 3, or another label could be say 2, 1, 3, or something like that. So basically, we're representing each instance by a vector. And I will actually talk more about this in the next lecture and their applications. So let's talk about some real-life applications before we go into the mathematics. And the first example that I will give is Google News. So if you open Google News, and in the, say, the science section, you see a bunch of clusters of news articles. So there are not one article, it's a bunch of articles clustered into one group. So for example, if you are interested in moon toilets, you can open this group, and there are 4 separate different articles. So if you want to read all of them, you can, but they are most likely very similar, so you only need to read one of them. So if you look at the titles, some of them are calling it a moon toilet, some of them are calling it a spaceship toilet, but in any case, they are covering the same topic, so and they are grouped into the same group. And you can look at all the groups. If you look at another group, it contains a few articles as well. And the group names are very good as well, but we don't need to do that here in clustering. And so in clustering, we just need to put articles into groups. So instead of giving you a bunch of independent, unrelated articles directly, you need to figure out which ones are similar, which ones are covering the same story, the same topic. Uh, Google News does this automatically using some unsupervised learning algorithm. So that's basically the idea. And similarly, you have Google Photo, which you put photos into not directly into groups, but Google Photo can automatically put your photos into groups. Say photos containing people, photos containing things, objects, and those ones are actually more like supervised learning because we are just classifying whether a photo contains the people or not. But unsupervised learning is more like I put similar photos together into groups and independent of actually labeling them as, say, people or objects. And the third application is image segmentation. We talked about this already, but let's talk about it again. So image segmentation is basically grouping the pixels into groups, and one group should represent one object. So there are two parts of the task. The first part is unsupervised learning. Basically, given the pixels, we put them into groups. Which pixels belong to the same object? So that's the unsupervised learning part. And the supervised learning part is given these pixels of a single object, we need to label them into one of the classes. So here we actually need these names. We need to give the algorithm the labels of existing objects. Otherwise, they won't know like what is a car and what is a traffic light. So again, two parts. Giving them names is supervised learning, and just putting the pixels into groups is unsupervised learning. Okay, so the last one is text processing. So we talked about NLP already, but as you saw in P3, if you want to represent each word by that one hot encoding, then each word, there are lots and lots of words, and each word is like 001 and 000. There are lots of zeros. There are m of them, and m is the size of the vocabulary, which is usually huge. So each feature vector is kind of huge. So if we can group them into groups, that's one way. We can group them into noun, verb, and so on. But also we can just reduce the dimensionality and put them into shorter vectors. So that's an example of unsupervised learning. And here, we will actually talk about PCA in the next lecture, but the main idea is we are putting similar words closer in a lower dimensional space. So for example, originally there are so many words, so each feature vector is very, very long. But here, after we apply PCA or unsupervised learning algorithm, we convert them into a three-dimensional vector with only three values. So basically, instead of this long vector, we only have three values, say 0.1, 0.2, 0.3, and a vector like this could represent one single word in the dictionary.